Hi, welcome you all for this video on Module 3 as per the VTU syllabus, which is on electrochemical machining and chemical machining. In the last video, I was discussing about the ECM tooling techniques, introduction and other things which I had discussed even in the first and second video. Let us move to the electrochemical machining tooling systems or tooling techniques. The tool used in the ECM process is approximately the mirror image of the shape to be machined in the workpiece. Hence, the tool is properly designed in size and shape so that under specified machining conditions would produce a workpiece having a prescribed shape and accuracy. That's why generally the undersized machining of the tool is very important, so that when machined on the workpiece the exactly or accurate shape or with the near required tolerance can be achieved on the workpiece. Further, the shape has to be maintained clearly, to a more accurate and precise manner. Further, the tool should be having a very good surface finish, so that the image which is obtained on the workpiece also possesses the similar kind of surface roughness or surface finish. If the surface roughness of the tool itself is having higher side, then obviously the surface which is obtained on the workpiece or machined surface on the workpiece will be of a higher values. That is, the suppose surface finish is being obtained on the machined quality. So that's why the surface roughness of the tool is also very important. So ECM tooling is about nothing but the tool of shape and dimensions has to be maintained or has to be made such a way that it is having a mirror image of the desired shape and dimensions on the workpiece. Further, the size and dimensions has to be maintained as an undersize, so that the nearly equivalent or nearly similar same size and dimensions are obtained on the workpiece. Electrolyte through electrode and insulated electrode. These two types of electrodes can be used. Nothing but the two types of workpieces can be used. One is through the tool itself, the electrolyte is being impinged or it is being sent to the working zone, that is machining zone, where the in the first diagram we can see here. Here we can see the workpiece when the tool is moving, that is tool is moving towards the depth of the workpiece. The there is a peak which is being observed at the center of the tool. That is nothing but the electrolyte is passing through the tool at the middle of the tool or at the center of the tool, a hole which is provided in the tool. Further, the flow electrolyte will flow on either sides or making a peak at the center. That is, at its center, the machining will not happen on the workpiece. So, because of this reason, there is every chance that even electrolyte will flow in. It has to exit from the workpiece itself. So when it is going to exit, again it is going to cause some amount of material removal. So obviously the hole will not be in exactly a cylindrical manner, whereas the tapered section is being obtained on the workpiece. That is when an electrolyte is passed through the electrode at its center, and the tool is not having any insulation on its circumference, that is on its walls, outer wall. Because of that, the machining is going to happen, because it is nothing but the material removal because of the affinity, the ion affinity here. Because of the same reason, the material removal will be more at the entry side of the hole, when this side is protected, so that the ion movement or affinity is being controlled on the outer walls of the tool. Then obviously based on that we can obtain a better holes, that is being achieved with the help of an insulated hole. The insulation is provided on the outer walls of the lateral walls on the tool. By that way, the material, the ion affinity on the walls of this tool is being controlled, because of which the hole which is obtained by machining of these kind of tools will be narrow. That is a perfect cylindrical kind of tool, nearly perfect cylindrical hole can be achieved. And the peak is also can be controlled, but only the major problem here is the peak, which is very which is to be monitored and which is need to be controlled. Actually, in general machining process, this is being removed or in the secondary machining operation. The third one is like a streamlined electrolyte flow. So here we can observe the peak which is being which is obtained in the last diagram, the second diagram, that also can be minimized with the help of the tool tip by providing the extra insulation at the tool tip. So when the tool tip is provided, it causes the electrolyte to flow in a maximum manner, so at its bottom, so that the material is being removed with the minimum peak at its center. So this kind of electrolyte flow, we call it as a streamlined electrolyte flow. In the last four diagrams, we have seen that electrolyte will flow into the tool, or from the center of the tool it will flow into the workpiece and exit from the outside the tool. Whereas in this case, this is a one a reverse process, or we can say a reverse of the other processes which we have seen in the last slides, where the electrolyte is made to flow from the outside and exit from the center of the tool, so that the electrolyte will flow from its outermost side and will flow into the tool and will get exit from the center of the tool. It provides the again a better cylindricity of the hole, but nothing but the and narrow holes can be obtained. But again, it has got its own disadvantages, like it is very difficult to proper flow has to be maintained. It is very difficult to control the flow of the electrolyte. All those things are again some of the challenges which lies with this electrolyte flow arrangement. Proper electrolyte circulation is essential, which you have seen even in the diagram. Proper electrolyte circulation is essential for accurate machining in ECM process. The tool must be properly designed to permit a uniform electrolyte flow in all machining areas, as sufficient or excessive flows uh, produce undesirable effects during machining. There are two arrangements for the flow of electrolyte in ECM process. One is divergent flow and second one is the convergent flow. That is a divergent flow, which in the first figures which we are discussed, that is what we call it as a divergent flow. The electrolyte is made to flow into the center of the tool, and when it is getting exit, it is the electrolyte will get diverged, and through the walls, over the walls of the cylinder or a tool, the electrolyte will flow and get exit. Whereas in the convergent flow, the electrolyte will flow from the outside and get converges at the center of the tool, and get exit from the center of the tool. This is what we call it as a convergent flow process. So these are the these are the different techniques which is being adapted for the ECM tooling. Next, coming to the process characteristics. Generally, when I mention about the process characteristics, we generally discuss about the two important thing is one is material removal rate, second one is the surface finish, because they do indicate the quality of the machine area or machined workpiece. So machine quality is being denoted by these two parameters. Further accuracy is also another such important characteristic. Material removal rate. Here MRR mainly depends on the feed rates, which determines the current that passes between the work and the tool. So yeah, as much as a higher amount of energy is available at the working zone, that much of material is being removed. So as the tool approaches the workpiece, the length of the conductive current path decreases and the magnitude of the current increases. A stable cut is established when the current is just sufficient to remove the metal at a rate corresponding to the rate of tool advance. Uh, and a proper control has to be provided to maintain the fixed spacing to facilitate highest MRR. Coming to the accuracy, some of the factors which governs the accuracy and surface finish are like one is machining voltage. The voltage variation changes the surface texture as a higher voltage makes more overcut and vice versa. Feed rate of the tool. This also has the same effect as that of the voltage. Third one is about the temperature of the electrolyte, and fourth one is the concentration of the electrolyte. So let us consider the first one. As I mentioned about the energy based on the energy which is available, the material removal rate will be higher. Nothing but when the higher amount of energy is available, obviously it will cause the larger replacement of the material on the workpiece surface. So the crater's size will be larger. The crater size will be larger for the maximum material removal. When the diameter of the crater get increases, obviously the surface roughness also get increases, because it increases the unevenity which is present over the surface of the workpiece. That's why generally the surface roughness also get increases with the increase in the current density or nothing but the energy availability at the surface of the workpiece. The next one is about the because of that reason, because of higher energy available, the surface roughness also get increases. When the temperature when the current energy which is available at the machining zone get decreases, the material is removed with a smaller amount per instant. That is nothing but the crater size which is being formed on the surface of the workpiece due to the removal of the workpiece surface material, or nothing but the smaller craters which are formed because of the replacement of the material from the workpiece surface. So such a number, infinite number of small craters will attach together and form the surface over the workpiece. And because of the smaller crater size of the small diameter craters, the surface finish which is obtained will be very good, or nothing but the surface roughness will fall down. The unevenity which are present over the surface will also get decreases. Next one is about the feed rate of the tool. It has also got same that of the voltage. That is, as the feed rate get increases, the amount the affinity towards the material removal, nothing but the ion replacement from the surface of the workpiece also get increases. When the feed rate is slow, that is feed rate is on the lower side, the affinity also gets a minimum value. So because of which because of less affinity towards the replacement of the material from the workpiece surface, the smaller craters are going to form, or nothing but a better surface finish can be obtained. So but at the same time, though we cannot consider only a surface finish, we have to make some compromise with the surface finish and also with the MRR. So to obtain an optimum surface finish and within a stipulated time, the material has to be removed, and optimal conditions of the machining parameters like current and other voltage and other values has to be preset. Next is about the electrolyte. The higher temperature of the electrolyte will catalyzes the reaction which is present on the working zone, or which is existing in the working zone. The lower the temperature will reduce the catalysis action, or nothing but reduces the number of reactions which is going to occur on the surface of the workpiece. Next, fourth one is about the concentration of the electrolyte. As the concentration of the electrolyte get increases, obviously the number of ions which are present for the further removal of the material from the workpiece also get increases. As the concentration goes on to the lower side, the obviously the electrolyte will also get also electrolyte will possess the lesser capability to remove the material. So concentration should be as high as possible, at the looking at the safety of the operators. Next is about the process parameters. In the ECM, that is electrochemical machining, the important parameters can be: one is current density, second one is the tool feed rate, third one is gap between the tool and the workpiece, fourth one is velocity of electrolyte flow, fifth one is type of electrolyte, its concentration, temperature, and choice of electrolyte. So let us go with the first one, current density. The current density increases, the increase in current density, obviously, as I mentioned already, the increase in current density will increases the availability of energy for the removal of material from the workpiece surface. That is nothing but the material removal rate also goes on increasing. Further, with the further increase in the current density will again may cause damages to the equipments. That's why a controlled higher current density is necessary to favor the higher material removal rate, but also need to consider the required surface finish. Based on that, the optimal current density value has to be set or need to be considered for operation. Next is about the tool feed rate. Tool feed rate is also works in the same manner. The higher the material feed rate, the better will be the material removal rate, poor will be the surface finish. But at the same time, where higher material removal rate is the many a times desired. Secondary finishing operation is done to remove the surface material from the workpiece, so that a better surface finish can be obtained. And then gap between the tool and the workpiece. The tool and the workpiece, the gap, which we can call it a standard distance or a gap between the tool and the workpiece, has to be maintained in an optimal condition. Too nearer will cause the spark may not get generated, or the reaction may not be facilitated for easily. But at the same time, again, when the too far of the tool and the electrolyte, workpiece, will cause the will reduces the ion movement from the tool to the workpiece, or nothing but the material removed from the workpiece surface. So because of which the material which is being which is desired to be removed from the workpiece surface also get reduces. Or again, with too small gap also may cause the spark, which may cause the damage to the whole equipments. Velocity of the electrolyte flow. The velocity of the electrolyte flow need to be on a higher side, because whatever the material which is being removed from the workpiece surface, it will get precipitated even in the electrolyte. Uh, the continuous movement of the electrolyte in a certain velocity, we can say, because of which the debris which are being formed also get increases. So flushing away of the wear debris or nothing but the machining debris is also a higher important factor, which or a vital factor which plays a very crucial role in the producing the better surface finish or better quality workpiece surfaces. The fifth one is about type of electrolyte, is concentration and the choice of electrolyte. The type of electrolyte and its concentration, again, the concentration based on its concentration, number of other factors which are going to depend. Like higher the concentration, the more number of ions. But at the same time, when it is being higher the concentration, more amount of material removed. But at the same time, on other side, the higher the concentration, which may cause damage to the operator. That's why the higher the concentration has to be considered such a way that it is not to be a hazardous for the uh, operators or the labor skillful laborers who are working with the ECM tools. Again, temperature, the higher the temperature, the catalysis action will go take on, and because of which the acceleration of the chemical reaction will occur, and further increases the removal of material. And the choice of electrolyte, again, different types of materials are suitable for different types of electrolytes. So based on the type of workpiece which is being used, based on that, the suitable or appropriate electrolyte is being chosen. Further, tool feed rate is about zero point 0.5 to 15 mm per minute, which is an optimal value of the tool feed rate which is being employed. The current density, as I mentioned, it is simply the current can be passed into square inch of work area. At low current densities, MRR is low or small. At higher values, the MRR will be higher. Gap between the tool and the workpiece are positioned as close together to encourage efficient electrical transmission. Small gap results in higher current densities and more MRR. The gap size should vary from 0.25 to 0.76 mm, and gap is a gap of 0.25 mm is often used. It is also important to maintain a uniform gap between the tool and the workpiece. Any physical contact of the tool and the workpiece will cause serious damages to the whole equipment. Velocity of the electrolyte flow, it should be between in the range of 15 to 60 meter per second. If the electrolyte flow is too low, the heat and the byproducts of the electrolytic reaction build in the gap, causing non-uniform material removal. Further, high velocity will cause cavitation. That is another very important serious issue, that when the high velocity fluids are flowing over any kind of surfaces will causes the cavitation. In the same way here also, an electrolyte, when it is made to transport at a very higher rate, it will cause the uh, bubbling or nothing but the cavitation on the tool itself, so that the tool also get worn out. That's why an optimal value of velocity is also need to be maintained. Types of electrolyte, like material NaCl and NaNO3. Electrolyte temperatures, it is in the range of 20 to 50 degrees Celsius. Flow rate 20 liters per minute for to 100 amps current, a very high current. And pressure 0.5 to 24, 20 bars. Dilution is about 100 grams per liter to 500 grams per liter. In this table, we can see sodium chloride, potassium chloride, and sodium nitrates. This can be used for a workpiece like steel, iron-based alloys, and steel alloys with nickel and cobalt. Whereas sodium chloride, potassium chloride, and sodium hydroxide also can be used for aluminium and alloys, copper and alloys. Sodium chloride and sodium nitrates, they can be used for brake cast iron. Sodium chloride or potassium chloride, they can be used for titanium alloys. These are some of the physical parameter variables which can be considered as optimal within the range. The general machining is being done. ECM machining is done. Tool and insulation materials. Insulation is also very important in the control of electric current, because high current is being employed here. Generally, a simplest method of applying insulation is by spraying or dipping. Teflon, urethane, phenolic, epoxy powder coatings, and other materials are commonly used for insulations, and sprayed or dipped coatings of epoxy resins are amongst the most effective insulating materials. Accurate advantages: accurate shape with better surface finish can be obtained. Machines complicated shapes in single pass. Capable of machining metals and alloys irrespective of their strength and hardness. There is a little or no tool wear. Process can be easily automated. Good surface finish, accuracy and tolerance. Low machining time. Deep holes can be made by this process and suitable for mass production applications. So coming to the limitations now, ECM is mainly suitable for only metals or nothing but electrically conductive materials. Uh, they are high electric power is consumed, so high amount of energy is being utilized here. Maintenance cost is also high, because high maintenance is a necessary aspect here. High tooling and setup cost, it increases the initial cost of the whole setup, or to establish a ECM setup. Post machining and cleaning is a must to reduce the corrosion of the workpiece, or else the whatever the chemicals which is being used during ECM will cause the corrosion after machining, especially on the machine surface. It has it possesses inability, or it is it is not able to machine a very sharp edges or corners easily. So it is incapable to machine a sharp edges or interior edges especially and corners. It is limited for mass production because of high tooling and setup costs. As I mentioned in the fourth point itself, it is having causes nothing but high tooling and setup costs or initial cost is very high. So obviously we cannot go for a single component production because it will finally affect on the each component cost. That's why mass production is better. For a mass production, ECM tooling, ECM machining is a better alternative. Applications: aerospace industries, machining gas turbine blades, airframe component fabrications, honeycomb aircraft panels, jet engine blade airfoils, manufacture of general machine parts, thin wall mechanical slotting, difficult to machine hollow shafts, chain pinions, internal profile of internal cams, driving joints, pump glands and impellers, connecting rods, hydraulic spools, gear wheels, facing and turning complex 3D surfaces, die sinking, particularly deep narrow slots and holes, profiling and any odd shape contouring, multiple hole drilling, trepanning, broaching, deburring, grinding, honing and cutting off. These are some of the applications of ECM process. Thank you. Regarding the ECM, I think I have covered a lot of the aspects which are possible and limited within the scope of VTU syllabus. If you have got any doubts, please post it or please mail it to me so that if possible I can attempt to answer those queries. I have used many resources from the internet as well as from the different textbooks for preparing this teaching material. I acknowledge all such sources and also I don't claim any originality or novelty in the preparing this teaching material. I thank to all such sources. I also thank you all for patient listening and yes, thank you. Have a nice day. If possible, if you have any queries, please try to contact me. Thank you. Thank you all.